planetary rotation and plasmasphere. We have said that the plasmasphere is a result of the planetary rotation and the convection of plasma coming from the tail of the magnetosphere. Now here in this picture there are two things. One is the plasma rotation, atmosphere or near the magnetosphere, and the other one, that the flow coming from your right, is the flow that is because of the reconnection that takes place at the tail of the magnetosphere. That is the plasma convection in the magnetosphere. What we see that there are two kind of flows and they are overlapping one to the other. And whichever strength is more occupies the space. Here you can see that the plasma flow from the tail of the magnetosphere cannot continue to move towards the center of the Earth because of the rotation, that the plasma flow is being dragged away by the rotational motion. This actually brings out a boundary at which this plasma flow cannot enter, and there is a stagnation point which appears on the downside of the magnetosphere. So in the downside, there is a stagnation point. You can see cross null point like things where the electric field associated with the rotational motion and the electric field associated with the plasma convection get cancelled. And therefore there are two things. One is the closed ones and open ones. And there will be a density difference, sudden density difference on the boundary. And this boundary would be called the plasma pause. And there is a sudden density changes inside. The density is associated with the plasma related to the or originated from the atmosphere of the planet. On the other side, the plasma density, which will be associated with the plasma that is coming inside the magnetosphere through the tail. So there would be, if one really plot the density in terms of the radius, then there will be a sudden drop in density gradient. And this density drop is known as the Carpenter's new, because the Carpenter is a scientist who was able to first determine this plasma pause or determine the density drop by looking at the Whistler mode data. Whistler mode is a wave which is quite active in this plasmasphere, and one can find out the density from the Whistler mode wave tracing. If you can trace, then from there you can find out the density, or you can determine the density, and it is shown that density is not continuous in this particular boundary. There is a drop in the density gradient, and therefore this is the signature of the plasmasphere. Now, if one get a little bit mathematics on it, so rotational electric field is given by the rotational velocity cross magnetic field. As usual, E is equal to minus V cross B by C. So here in this case, rotational, that is the velocity associated with the plasma or the rotation, and the magnetic field crossing each other will give rise to a particular value. On the right-hand side, you can see that what is V. V is essentially the velocity, circular velocity, because of the rotation of the Earth, and the rotation frequency is omega p. and its direction is towards the north, and that crosses with r. R is the distance from the center, and omega cross r gives the velocity, and if you cross with b, you will get the eco-rotation. And this is simple, something simplification is done because we have to change the velocity, sorry, not the change the velocity, magnetic field, and that magnetic field can be expressed in terms of magnetic field on the ground, assuming that B is equal to V01 V0 by R cube. And if R is measured in terms of the radius, then I divide it by RP, and that RP goes up. And if you plot that in, or if you put that in the expression for B in that equation, we'll get the rotational uh, electric field there. And the convective electric field is given by the velocity is solar velocity, and magnetic field is the magnetic field associated with the infrared magnetic field, assuming that that is the kind of velocity entered inside the magnetosphere. So we can find out the convective electric field, and when you balance these two electric field, then we get RS will be in terms of the convection electric field, radius of the planet, and magnetic field B0 on the ground, and this omega p is the rotational frequency. If one plots this, if put all these values in it, then it is found that RS could be almost equal to 4 art radii. So that is the distance of the plasma pulse from the center of the Earth, and that is given by this relation. It is not always constant because of the fact that convection electric field is not always constant, but other values are constant, and so therefore the distance of plasma pulse will depend upon the convection that is coming from outside, or the magnetospheric convection. So that is the kind of plasma pulse, plasma sphere, and therefore we are ending up with in a magnetosphere. In the structure, we are ending up with several things like in the magnetopause, magnetoseat, cusp region, magnetotail, then plasma sheet in the equatorial plane, then convection. Now we get the plasma sphere and the plasma pause. All these are associated with the structure of the magnetosphere. It planet having intrinsic magnetic field, and their configuration of the magnetic field is similar to that of the Earth. Now we will move to, we'll come back to this case again. We'll come back to the magnetospheric diagram by dividing thermodynamics and thermodynamics. But here we would like to get something about the radiation belt. There are, as you can see in the picture, there are two kinds of radiation belts. One is the inner radiation belt and the outer radiation belt. And they are the region where particles of high energy are trapped. Therefore, in the radiation belt, we'll have to understand different kind of mechanism by which the particles are trapped, and they remain trapped for a longer time. What are the conditions that the particles remain trapped for a longer time? Then the acceleration of the particles, loss of the particles, precipitation of the particles from um, the magnetosphere, outer region, then sources of observed particles, effective tapping time, and diffusion of particles, acceleration of particles. These are all the things that would be needed to be studied in this region, both in the case of inner radiation belt and outer radiation belt. We'll come to these two regions later on, and we'll get this picture back again after we study a little bit of the particle dynamics in general in presence of dipole magnetic field. But Earth is a dipole magnetic field so far as we are near to it, and therefore the motion of the particles will be determined, will be controlled by the magnetic field of the Earth. Now, of course, you know the general, you have learned, of course, the particle motion in presence of magnetic field and electric field, but I would like to make a little quick um, revisions for that so that we remember all these things again slowly. Now, this is the simplest case. The single particle motion in electric and magnetic field is given by or is controlled by the Lorentz force, and that force is written there. Force is Q E plus 1 by C E cross B. Now, therefore, the motion of the particles will be determined by that equation. Now, we can study this by considering several independent conditions so that we can understand particle motions a little more clearly. The first one is the simplest one. If you have the electric field in the medium, then you get m dv dt is equal to QE. To solve that equation, in this particular case, I have written that the V is along the E is along the direction of Z. So dVz dt is equal to QE, and if you integrate that, you get Q by m Et plus Vz0. Well, Vz0 is a initial value for Vz. Now, what it means that you get the particles accelerated by the electric field. One thing you must have noticed that it depends upon the mass and the charge of the particles. So the acceleration for the protons takes place in the directions of the electric field, and acceleration for the electrons in the opposite directions. Plus, acceleration because of the protons and acceleration due to the electric field, but electrons are different because they are mass dependent. Now, one thing which, of course, you know that dVz dt can be written as minus Q by m electric field, and that is gradient of phi and delta phi delta z. And if you do little bit of the calculations, then you will get the equation d dt is half mvz square plus q phi is equal to 0. What it's essentially meaning is that the energy due to the particle, kinetic energy due to the particle, and the potential energy will remain constant during its motion. Next comes that there is no electric field, but there is only magnetic field, and in one direction, which is in z direction, I've written in my picture, and I'm going through rather quickly. So because you know all this, I hope you know all this, but I'm going through this because I need it. M dV dt is Q V cross B by C, and obviously you can see if you have a dot product with V, then right hand side goes to 0. and left hand side becomes ddt of half mv square is equal to 0. That essentially means the energy remains constant. What is physically also you understand this because of the fact that the force that is acting on the particle is perpendicular to its motion. And when there is a force perpendicular to the velocity, its motion, there is no work done. And if there is no work done, then there is no change in energy. So that's the physical meaning of that. And therefore, we can proceed further. Now, if you can have this equation in three components, Vx and Vy, and I've written there Vx, Y, Vz, and B0 is only in the Z direction. You get two equations, m dvx dt q by c, Vy, V0, m dvy dt minus q by c, Vx, V0. If you combine these two, you'll get the equation d2vx dt square minus qb0 by mc whole square vx. I write down now qb0 by mc as omega, and that can be written as now minus omega square vx. Now this is the equation which determines the simple harmonic motion. Solution is given by vx is equal to vx e to the plus e to the power I omega t. Above that plus minus you have, and that therefore gives the motion of the, you get a circular motion, and the circular motion is different for the protons and electrons. If q is positive, then it left hand rotation, and if q is negative, right hand. So the electrons and protons, of course, they move along the direction of the magnetic field, but their rotation sense is different. One is the left hand, if you have a left hand side, if you left hand motion, and for the electrons is right hand motion. So this is the kind of motion of particles. We should remember this because this will determine sometimes the surface that produced by the particle motion, or in a circular, it enclosed magnetic field, and that will be a surface enclosed by a magnetic field, and there is a kind of conventional direction of the surface elements, which will come later. Oh, you can solve these equations in a different way. If you want to have the really circle, then you can have Vx, the solution can be written as a cos omega t plus b sine omega t. At t equal to 0, we assume that Vx is Vx0, then other term you get 0, so A is equal to Vx0. Similarly, then you can make the derivative of that, you get to the right hand side A omega sine omega t plus B omega cos omega t. There is a negative sign there. Now, dvx dt, you can just replace by qvy from the first equation itself. Then you get this equation, and there you can find out now at t is equal to 0, vy is vy0, and vy0 is b. So A and B are then determined. So then Vx is equal to that, Vy is equal to this. If you square and add them together, then you will get the Vx square plus Vy square is equal to V perpendicular square. Furthermore, this is in the velocity space, but we want to know the actual radius in our space, ordinary space. and for therefore we have to go from the velocity space to the ordinary space, and then you can write dx is dx dt, and then right hand side is there. You can integrate, then you get x. If you integrate cos omega t, you get sine omega t by omega, and integration of sine omega t will be given by cos omega t by omega with a minus sign. Similarly, you can get y. So x square plus y square, you get v perpendicular square by omega square, and therefore you make a circle, and circle with a radius v perpendicular by omega. It has particular name, and that name is Larmor radius. So in this process of the magnetic field, motion of the particles in constant magnetic field, we get two parameters. One is the Larmor radius, and the second one is the gyro period. These are important parameter to remember, or expression to remember later on. And I'm refreshing myself and going through that. And if some of you need some refreshment, then you can also get it. Now, next is the E is non-zero, B is non-zero, and assume that E is perpendicular to B. Now, here in this case, the proton motion is shown in the left hand side, as well as electron motion, and they are different than the one that we described earlier. On right hand side, we see in the y direction electric field, z direction B0. In the left hand diagram, I put vertically y direction, y is in the vertical direction, B is coming out of the screen. So in this case, now let's describe physically what happens. Suppose you start off with a particle, say no velocity. But as soon as you put that in the center, you see that it will see the electric field. As soon as it sees the electric field, proton will move towards the directions of the electric field, that means towards the E direction, and try to go in that direction. But as soon as it attains some velocity, now as soon as it attains some velocity, it will see the magnetic field. So it will try to rotate. It try to go the helical motion. So it try to curve, then out. And it goes like this. And then when it comes to the point again, suddenly it says that there is no velocity. And since there is no velocity, therefore there is doesn't see the magnetic field. It sees the electric field again. So it goes up and goes on like this. So the proton moves like this, and the electron moves in the opposite direction. So both the protons and electrons move perpendicular to both electric and magnetic field, as it's shown in the picture. Now, when you have the initial particles with initial velocity, let me see, I didn't say the name of the card, that is that one obtains here, is the name of the card which is generated by the proton motion or the electron motion is given by cycloid. And actually cycloid is the motion where if you fix a particle in the tire of your cycle, when it makes one complete cycle, it will make that half cycle made by the proton. So that is actually the cycloid motion in in geometry. Now, if you have initial velocity non-zero, then when it comes first to the y-axis, it still sees the magnetic field, and therefore it tries to rotate. But by doing that, the velocity decreases, and therefore velocity decreases because electric field in the opposite direction. Velocity slows down, and therefore it wants to make a round circle, but that circle becomes small and then goes out and then becomes again this kind of motion is produced. So this is the card which is called torchite, and for electrons it goes in the opposite direction with a some smaller circle because the radius, larger radius for protons and electrons are different. For the protons it is large because of the mass, and for electrons it is less. Now it can also be obtained mathematically. If you write down m dv dt q e plus v cross b by c, then one start with trial and error. One assume that v is equal to v1 plus vd, where vd is assumed to be c e cross by b squared. It is because of some intuition, e cross b by b squared, and put that in that equation back. If you put that in the equation back, you write v is equal to v1 plus vd. So one term will be v1 cross v, the other term will be vd cross v, and then vd cross v will be simple. You can make simplify, and you will find out finally an equation m dv1 by dt is equal to q by c d1 cross b. I did not do the simplification. Little bit algebra, you can do it. It's very simple, and therefore we get back the gyro motion with v1 and plus drift because of the electric field. So we have gyro motion plus drift, and drift is given by vdc e cross b by b square, which you can see independent of charge and mass. So the electrons and protons drift in the same velocity. And that's very important. And in this case, therefore, there is no current because electrons and protons move in the same velocity, in the same direction, and therefore there is no current. Now, we can get something more out of this simple expression. We can write electric field in terms of force, and force is given, electric field is given, electric field is given by the force by Q. So Q is replaced by F. Then Vd, which is given by C E cross by B square, E can be replaced by F by Q, and then you can see C F cross B by QB square. Now it becomes dependent on the charge. So in this case, the electrons will move in the opposite direction to the protons, and therefore some current can be produced. Let's see if m is equal to mg, gravity, then Vd can be written as c by q by b square, and that you can see that it depends upon both mass and charge of the particles. Obviously, protons, VD is large, or electrons, VD is small. And I'm sure whenever you see this expression, C by Q and G cross B by B square, you probably remember something that happened in the ionosphere. You probably remember the Rayleigh Taylor instability, which is driven by the gravity, and there the electrons and protons, motion of the electron and protons due to gravity gives rise to an electric field, and that electric field is responsible for the generation of the instability, which finally leads it to the spread F. Now another important parameter is called the magnetic moment, and magnetic moment actually is like defined by the current into area, current derived by the current obtained by the particles going around the magnetic field, and the area it describes when it completes one cycle. So that is given by current is obtained if you know the number of turns per unit time. So it is associated with the time, and that will determine how many turns it takes place in unit time. So that would be given by Q by C, and 1 by T would be given by the turns, number of turns, and that is defined by the time, 2 pi by omega, and the area is pi r L square. RL is the thermal radius, pi r L square is the uh, area of the circle, and that you can write down on that side, and you get mu is equal to W perpendicular by B. Very important parameter as far as the magnetosphere is concerned. So we know now what is the expression for the magnetic moment. Magnetic moment is determined by the perpendicular velocity, perpendicular not velocity, perpendicular energy divided by magnetic field at any point. So that is the magnetic moment. Now let us go to some other phenomena or some other motion of the particle which will describe the characteristics of magnetic moment. We can have a magnetic mirror or a bottle which this appearance, this structure of the magnetic field was very important for even the confinement of plasma in the mirror machine towards the fusion. Initially we tried with this, with the mirror machine. Now here we have actually the magnetic field when you have divergence of B gives several components, 9 components, and we are here in the mirror only 3 components, Vx by dx, Vy by dy, Vz by dz. These 3 components exist, others do not exist. So the main field actually is Vz. So if you use our Maxwell's equation, the divergence of V equal to 0, you can express that in cylindrical coordinates, which I have written on the right hand side, delta delta r a r, delta 1 by r, delta delta theta, a theta, delta delta z a z. And if you put that in, we get an expression on the left hand side, 1 by r ddr of rbr plus dBz dz, which is equal to 0. Now we make some simplification, and then you can make the integration. When you make the integration, one thing you have noticed that I have taken delta b del dz out of the integral, and on the right hand side your integral is 0 to RL r dr. So if you integrate, now this is the integration, which then is given by RL BR. RBR is equal to RL square by 2, because R square by 2, limit is RL, RL square by 2, delta BZ delta Z with a minus sign. So the BR comes as minus RL by 2 dBz dB dz. So that is the R component of the magnetic field. We get the R component of the magnetic field in this case from the equation, Maxwell's equation, and this is expressed in terms of dB dz. Interesting. Now, if you know dB dz, you can find out Br. So we can write down the equation of motion, the parallel component, and dV parallel dt, q by c v cross b parallel, and then you get q by c v perpendicular Br, and q by c v perpendicular Br is replaced by what we have got earlier, RL by 2 dBz dz, and finally you get that is equal to minus mu dB dz. Now what I wanted to say that the mass into acceleration is the force, and whenever you have slowly varying function of the magnetic field dB dz, and the force is given by minus mu delta bz dz. Now this could be in general true, and in general we can write down minus mu gradient of B should be the force. Now one thing I'd like to mention again, that we have taken delta B delta Z out of the integral because of the fact that it does not change in the region of normal radius. In that normal radius, delta B delta Z does not change, and therefore it can get out of the integral. So we go back again, and dV parallel dt is equal to this, and that some simplification, dV parallel dz dz dt, which v parallel dV parallel dz minus mu like that, and half mb parallel squared with d dz, you get minus mu delta b delta z, mb parallel squared, it is a make w parallel mu minus mu dB dz, but here the total energy is conserved, as I have mentioned at the very beginning. So long as slowly magnetic field is there, the total energy is conserved, and therefore the dW parallel dz is equal to minus d perpendicular dz, and therefore in the left hand side we change it. What I want to say is that d mu dz equal to 0. What I want to emphasize in all these calculations, which will be quite boring to you at the moment, but what I want to emphasize is that the mu is a constant. The magnetic moment is a constant, and it is an adiabatic invariant. adiabatic in a sense that the magnetic field does not change during its motion extending to Larmor radius. So that is therefore the mu is an in magnet adiabatic invariant. Similarly, you can have the electric field with time dependent, then also you get an extra drift, and that extra drift is c square I m q by b square delta E delta t, dependent on mass and charge, and this contribute to displacement current in Maxwell's equations. You know, this can be, you can do this calculation again by going to the equation delta V delta T is equal to QE plus 1 by C V cross B. There you write V is equal to V1 plus Vd because of the electric field, which can be written as C E cross by B square, plus Vp, which is given by C square by QV square delta E delta T. Now if you do that, then you would be able to find out that you are getting then the equation dv1 dz is equal to q v cross b by v square, and therefore you will get the motion in three different ways. You get the gyration motion plus the motion associated with the drift because of the constant electric field and because of the electric field which is dependent on time. So that gives you, as you can see, the Vp here depends on the charge and the mass of the particles. Therefore, it produces current because for protons and electrons it will be different, and that produces a current. And therefore, you can look at the current that you have. J is equal to this. It's simply algebra. You go do that, and you get J is equal to mc square b square m delta E delta T. Now, if you have extra J because of the polarization electric field, then there will be some contribution to the Maxwell's equations. And the Maxwell's equation, you get that delta E delta T and Jp. J is the external electric field. Jp is the electric field that is produced by the polarization or electric field, time dependent electric field. You can simply write that equation here. We get 4 pi j 1 plus 4 pi rho c square by b square delta E delta T. That you can replace by epsilon. Epsilon is given by that part, and therefore you get delta D delta T. So what it is introduced at the dielectric nature of the plasma. In the case of when a time-varying electric field exists in a plasma, so you will get the plasma as a kind of dielectric because it has produced epsilon, which is 4 pi rho square c square by b square, and rho is the plasma mass density. B is the magnetic field. So you have now, I have rather gone through quickly on all these because I assume that you have done this in your course earlier. If not, it would be nice to go through it again. Now, if you have a slowly varying magnetic field in time, Bt, then we have delta B delta T minus C curl of E. And if the particle moves along the direction of the magnetic field with an electric field in it, then that energy associated with the particle would be given by Q E dot dl. That means Q is the force, dl is the element that it moves, and so the force in distance or will give rise to the work done, and that the work done is the energy, and that energy is represented by here Q integral of E dot dl. Now E can be this E dot dl integral. You can use the vector analysis, and you can see that that can be described as curl of E dot ds, and ds is the element of the surface produced by the particle enclosed in its own circle. So that is given by curl of E dot ds,